Hello everyone, this is Ahmed Shita. I will be the lecturer of core of this course, steel structure, design of steel structure, and today will be our first lecture, module number one, the title Introduction to Steel Structure. So our first lecture will be about the introduction to steel structure and the steel as construction material and the development of steel structure and so on. So this is the first picture. The title of this module is a stadium in China called Beijing National Stadium. Looks nice at night. So this structure is made of steel structure. So it will be good to uh, like see some beautiful steel structure like this one. And I will start with the unit description. So what we will do in steel structures course. So this will be like building on your knowledge, structure analysis, and material courses you have done before. So this unit will introduce the design of steel structure. Also, you will apply the Australian standard related to steel structure design, which is AS 4100. The new version is 2020, so there is a new version of the standard. So our rule is to apply the Australian standard to satisfy trends and serviceability limit states. Also, we'll learn about engineering drawing and how to convey engineering solutions to drafting personnel. Okay, the unit is consists of six modules. The first week is module number one, introduction of steel structure. Second one will be limit state design. Third one will be design of wing load. The fourth will be design of steel members subject to different training actions, extension members, compression members, members under shear, members under bending, and combined action. And module number five will be design of connection. Module number six will be design of portal frame, which is related to module number four, member members subjected to combined action. Those frame members are subject to column are subjected to normal and moment, and the girder are subjected to moment and shear. So these are combined action. There are some textbooks that you can use as a resources, which is Steel Designer Handbook and also worked example for steel structure according to AS 4100. The standard we are using are 4100 steel structure, 1170.0, which is design action, general principles, and also 1117.1, structure design action, part 1, permanent and imposed and other action. And the first standard we will use is 1170.2, which is also design action, wind action. So 1117.2 for wind, 1117.1 for imposed load, and 1117.0 is for general principles. Those are some references for the modules and the course content. You can also have a look at them. And there are some other online resources like One Steel and Australian Steel Institute. Okay, so these are the resources that we can use to understand the course or have more reading or further reading of the course content. Okay, so this is week one module. So this module will introduce the functions of steel structure and various construction materials. It also will discuss the advantages of steel structure over concrete and other materials and brief explanation of how the steel structure developed over the past few years. The module will also focus on the key concepts of the solution of steel structure elements and structure systems used in different types of steel structure, like main type, high-rise and low-rise buildings. And finally, there will be a hint about overview over the plate girders used in longer span building where we need large open areas. So in some cases, we need large span areas without any intermediate column. So plate girder will be used in this type of structure. The topics we have in this week will be introduction to steel structure, structural steel framing, and other structural steel elements. The objective we have in this week will be to know function of structure and different construction materials and the advantages of steel structure, structural steel over concrete. The second objective is to know about the development of steel structure. The third is the key concepts behind selecting steel structure elements. The fourth will be structure system of mill type, low and high rise or tall buildings. The fifth and the last one is use of plate girder in longer span structure. So we will start with the introduction to steel structure. So first of all, what is the function of structure generally? So the function of structure is to carry loads and transmit forces in variety of ways. Let's say in multi-story buildings, so wind, snow, and rain supported by roof and floor. Wind loads are resisted by external walls or cladding. Dead and life loads, including people, furniture, floor cover, machinery, and so on, supported by floor slabs and beams. All these loads are then transmitted to steel frame, finally to the foundation. So all the loads, whatever the loads is, wind, snow, wind loads, dead and life loads, will be transferred to the steel structure, superstructure, and then to the foundation because all the loads finally will go to soil. So we'll go to the foundation first and finally to the soil. We have different type of structures like bridges. So bridges supports deck allowing passage of pedestrians and vehicles. Dams hold back large volumes of water. Retaining wall which will prevent the slippage of embankment. Offshore structure carry drilling rigs, accommodate crews, helicopter pads, and resist action from sea waves and wind. Harbor docks and jetties which carry cranes and resist the impact of docking ships. So a lot of structure or types of structure that we can use or we need to construct for several usage in our life. So second point is the construction material used in this structure. So our focus will be on steel structure. So the material is steel. This is the most or the focus of our course. So steel is one of the most used material in the world. Mild low, mild steel or mild low carbon content. Mild steel, which has low carbon content, strong, cheap, ductile, and easy welded and widely used. So mild steel is the first type of steel we have, which has low carbon content, and it is strong, cheap, ductile, easily welded, and widely used because it is cheap. The second type of steel we have is high strength steel, which has high carbon content, greater in strength than mild steel, but the problem is less ductile. So the steel, because it is carefully controlled or has high quality control, so it has low variations in durability. So because it is like high quality in factories, so low variation in durability. The problem of steel are it has weak resistance to fire and also corrosion. So these are two main problems of steel. We have two types of steel sections. There are hot rolled steel and cold formed steel. Okay, so this is our first material. The second material is concrete. Concrete is a mixture of cement, water, coarse and fine aggregate, and some admixtures. The main advantage of concrete is that it is relatively cheap and widely available. It is the most common used material in the construction industry. Higher versatility, which can be cast in situ. The problem of concrete is it is weaker and has lower stress to weight ratio when compared to steel. So when compared to steel, the concrete is weaker in tension and in compression. Another problem which we're talking about is tensile strength is very low because it is only 10% of its compressive strength. So the tensile strength of concrete is only 10% of the compressive strength of concrete. One of the good things of concrete, it has good resistance to fire and very durable. So it has advantage over steel that it has good resistance to fire. The third material we have is the timber. Timber is natural material, naturally produced, so properties vary widely due to varying quality and the presence of defects. So it has a lot of variation because it's a natural material. The timber is normally stronger in tension than in compression due to the nature of the grain. So one of the advantages if it that it, the timber has higher tensile strength than compressive strength. We have two types, hardwood and softwood. Hardwood is short grain, not necessarily hard. Softwood is long grain. The disadvantage of timber are warping and twisting can be eliminated by using its laminated form. So timber has two problems, warping and twisting, but this can be eliminated by using it in laminated form. So to avoid the warping and twisting. Another issue is we need treatment to resist fungal attack. So it needs some treatment to avoid or resist the fungal attack. The first material we have is masonry, which is made of bricks or concrete or stone. The problem of masonry is it's brittle and weak in tension. The masonry can be made of clay shell. Engineering bricks can be the main load-bearing component in masonry structure with minimum guaranteed strength. So the bricks can be the main load-bearing component in masonry structure with minimum guaranteed strength. So strong enough to be the main load-bearing. Facing bricks have different strengths with better appearance. So engineering strengths can be used as main load-bearing, but facing bricks are like decorating bricks. not as structure or carrying element, load carrying element. The fifth material we have is aluminum. Aluminum is a pure aluminum is obtained from bauxite. They are often expensive to produce as well as soft as weak. So the problem of aluminum is it's soft and weak when it is and also expensive to produce and it is made of bauxite. To avoid this or to improve the probabilities of aluminum, magnesium is added. So magnesium is added to strengthen the aluminum. It has advantage that high strength to weight ratio compared to so it is better than concrete and has same advantage of steel that it has high strength to weight ratio. Also another advantage is ductile. Another advantage is can use aluminum to fabricate lightweight roof structure and window frame. So it has some application to produce lightweight structure. Also can be formed in complicated sections. So aluminum can also form complicated sections. The last materials we have is the composite material like fiber reinforced polymer FRP or fiber reinforced composites, glass reinforced plastics, carbon fiber reinforced plastic, and also there is a material called engineered cementitious composite ECC, which is a sort of fiber reinforced concrete. So there is a lot of material that contain like two or three other materials, so it's called composite material. These materials can be used in aircraft, automobile, and building. The problem of this or the drawbacks of these materials are they are expensive. Probabilities are not fully understood because consist of several materials. So the probabilities are not very clear. Need more study. So are the materials we have, and there is a video here talking about the comparison between hot rolled and cold forming steel. So it will be interesting to watch this video. And then we will jump to our next topic, which is development in steel structure. So in early steel structure were fully exposed and riveted connection without treatment were widely used. So at the beginning of steel structure, all the steel structure with riveted has riveted connection without any treatment. And also the form of structure was driven by its function. No special consideration was given to aesthetics. Rule of steel changed to time towards lighter envelopes and larger spans. So with time, the role of steel changes to improve the structures and to produce lighter weights and increase the spans of the structure. Structural framing, supposed to full view, has taken many forms: space frames, parallel vaults, cable stayed bridge, and cable net roof. So the structural framing has many advanced forms, like what I've given here: space frames, parallel vaults, cable stayed, cable net roof, suspension roofs, and suspension roofs. High visibility of structural framing desire more aesthetically pleasing connection. So the connection need to be more aesthetic Cost is kept down through well-designed connection, simplicity of detailing, and maximum possible repetition. So to keep the cost low for steel structure, the connection need to be well designed and simplifying the detailing and maximize the repetition. So you need to reproduce same structure again to make it cheaper. Structure framing becomes more attractive in terms of cost, reduced fabrication efforts, and increased quality engineering efficiency with time. So it become more common. Basic understanding of the behavior of structural steel and the use of design or modeling methodology would enhance the efficiency and economy of design. Finally, the design standard play an important role in improving the steel structure design and encourage engineers and designers to use the steel structure. The next head or topic is structural steel works, and here are some examples of structural steel works around the world that use steel structures or steel sections. So structural steel work is an assemblage of commonly used standard steel section connected by bolts or welding or combination of bolts and welding. So as you know, or we will see in the next lectures, we have some common like channel section, eye section, and so on. Some examples of the structural steel works: Hong Kong Bank, HSBC, and Petronas Twin Tower in Kuala Lumpur, and Sydney Harbour Bridge, and Golden Gate, San Francisco. The Golden Gate, San Francisco is an example of suspension bridge, and there are also some examples of cable knit roofs and also base frame structure. So all these images are examples of the structural steel works now, available now, or constructed now, which show how much is the development that happened to the structural steel or steel structure. The next point is steel as structural material. So steel as structural material is widely used metal. So structural steel is the widely or the most commonly used metal in construction compared to aluminum and other metals. Some advantages of steel are great strength, which permits heavy loads with small members and longer spans, good ductility at points of very high stress, such as the vicinity of the poles. Yielding of the material enables load redistribution. So steel shows good ductility, which help to redistribute the loads when yielding. Also high stiffness, so we expect small deflection or lower deflection. Ease of fabrication, so sewing, drilling, and flame cutting, bolting, and welding. Good quality control, because this in the factory, like manufactured in factories, so it has good quality control. Ease of alternation and extension, ease and speed of erection, and also relatively cheap compared to the advantage they give to the construction industry. The next point is comparison between structural steel and concrete. Because concrete is the most commonly used material, so we need to compare the steel with concrete. So when compared steel to concrete, steel is roughly 3 times denser than concrete, so steel is heavier than concrete. But for a given load carrying capacity compared to concrete, the weight of steel is one third, the volume of steel is one tenth, the cost is four times. So steel in weight to carry same weight or same capacity will be one third, and in volume will be one tenth, but in cost will be four times. So these two are advantage, but this one is a drawback. Concrete is preferred for construction or structures when dead load or on weight doesn't dominate. Example, walls, floor slabs on the ground, suspended slab with short spans. Also the second one, so this is the first preference. The second preference when heat and sound insulation are required because concrete has better resistance to fire. Steel is generally preferable over concrete for longer span, roof or bridge. Second is tall buildings and moving structure where weight is not favorable. Also, steel is often used with concrete, not only in reinforced concrete RC structure, but also in composite steel concrete construction. What is the composite steel construction? Is like for as example is structure steel beams, like again I beam or C channels, the standard beam, connected by shear studs so that the steel beam and the RC slabs behave as a single structure unit. So I will show you an example of this. So this is our structure steel beam, and then on top of this there is a slab. In this slab we have some shear studs and then a slab. So this is the RC slab. This is the studs, and this is the steel I beam. In some cases, when we need weight to be minimized, so aluminum or magnesium alloy or FRB or fiberglass carbon fiber may be used. Okay, so in some cases we prefer to use different material rather than steel or concrete. The last point in this comparison is steel is very expensive. Oh, sorry. This solution is very expensive. So using the aluminum and magnesium alloy and FRB are expensive. So need to be used only in extreme cases. These are some examples of composite materials or composite constructions. The first example is a steel bridge supporting the concrete deck. So this part is steel. This part is deck made of concrete. Here as well, the slab is concrete and the beams are steel. And this is a typical example of or typical cross section of composite beam. This is a steel section, I beam, and this is a reinforced concrete slab. And as mentioned before, this is a shear stud. Okay, the last point is the Australian standard 4100 steel structure. The new version or the latest version is 2020 version. This standard is deemed to comply, so need to apply or make sure that all our designs are complying with AS 4100. The standard set down minimum criteria for structure adequacy. So if you follow the structure or the design procedure of the Australian standard, so will like guarantee minimum structure adequacy for your structure. Provide acceptable methods of determining action, like forces, moment, and so on. Methods of performing structure analysis, sizing of members and connection. Also cover the material and workmanship requirements of the structure, quality testing and tolerances. This unit is generally intended to be used with 11 AS 4100 2020 steel structure. So as mentioned earlier, this is the latest version of the standard. Okay, now we will jump to our second part of the lecture, or second topic. Second 1.2 is steel structure, steel framing. The first point is the introduction, structure steel framing. So structure framing comprises all structure member and connection required for the structure integrity. As you know, to make a complete structure, we need members, column, girder or beam, and a connection. So the connection is this one and this one. So these are connection. So this all is the structure framing, including the members and the connection. Some common steel buildings are single-story dwelling frame, large mill building, low-rise framing, high-rise framing. The design principles of all steel structure are largely the same, so all of them quite similar, and they are mainly like design of member under tension, compression, shear, moment, axial, and combined action. So those are the the design criteria for members under several training actions. The second point we have is selection of structure steel framing. So a wide range of information is required for the selection of the appropriate system. So to make the selection or sizing of the structure steel framing, members and connection, a lot of information is needed, including site topography, location of adjacent building, surfaces and other constraints for the wind loads, foundation material profile, bearing capacity, types of footing for designing the foundation, groundwater level and drainage, terrain features for wind loading assessment. So this is also under wind. Access to construction equipment, building layout, column grids, minimum headroom, maximum depth of beam and trusses, possible location of raised bays, provisions of future extensions, loads imposed on structure, such as life load, machinery, and crane loads, material used in the building, envelope and floors, type and extent of building surfaces, ventilation and air conditioning, fire rating and method of fire protection, means of egress or exit, other statutory requirements. So all this information are needed to design the building and sizing or selecting the structural framing elements. In general, the number of framing elements should be minimized and the weight to be optimized for reason of economy. Often affected by the magnitude of horizontal load closely related to height. So the structural steel selection mainly affected by the magnitude of horizontal load closely related to height. So horizontal load including wind and earthquakes. Structure can be designed to resist horizontal loads by columns cantilever form footing, beam and post frames, shear walls, concrete or brick walls, rigid frame, rectangular frame or portal frames, bracing system or stayed cable, combination of the above method. Braced frame have two types, one way or two way are the most cost efficient. So braced frame is the most cost efficient system to resist the lateral load. However, bracing panels often interfere. Bracing panels often interfere with the functional layout of the building. The use of the rigid frame overcomes this drawback. So sometimes the bracing panel like obstacles the function or architecture use of the building. So sometimes we cannot use the bracing and we use rigid frame. In low-rise buildings, often single-story, workshop buildings and warehouses, the framing system often consists of portal frames in a transverse direction and the bracing panel in the longitudinal direction. So in the low-rise building will be like frames and bracing system in the longitudinal direction. So will be something like this. This is the short direction. So the frame is repeated and there will be like bracing in some base like this. Okay. So this is a low-rise building. A range of different framing systems are available for tall buildings where wind load is significant consideration. So in tall building, the wind is the most significant load, so need more attention. The third point we have is the mill type buildings. So the structural framing for mill type, medium heavy type industrial buildings are usually consist of series of portal frame bands parallelly arranged like this one. The portal frame resists all vertical loads and lateral loads acting in their plan. So is this our portal frame? So this frame carry all the vertical loads and lateral loads in their plane. So this in plane loading. But the forces acting in the longitudinal direction perpendicular to the frame out of plane load are resisted by bracing panel arranged at intervals. As in this figure here, we look at this figure. So all these in plane loads are resisted by the frame, also in this direction are resisted by the frame. But when we have loads in this direction, like perpendicular to the figure, like this direction, these loads are resisted by the bracing here, and also so and also the roof bracing here. So if this our frame and this is the next frame and so on. So any load in this direction like this will be resisted by this bracing. So the bracing, this is the bracing, will resist the wind load. There are some commonly used in plane framing systems. The first one is cantilevered column with simply supported roof trusses, as in the figure. So we have this is the roof truss, and this is the cantilever column. So it is fixed here and fixed here. So the moment on this column will be something like this because it's fixed at the bottom. So in this type of in-plane framing system, lateral loads, wind, earthquake, and plane loads are resisted by the cantilevered column. So all the lateral loads are transferred to the column. This is not sensitive. This system is not sensitive to the foundation movement or settlement. Another advantage of this system is the relatively easy erection, only one bend between column and roof trusses. So it's easy because only one connection between the roof and the column. Second type of frame or in-plane framing system is the rigid jointed frame with fixed or bend base. So in this system will be in this figure, example of this system. So as you can see, the connection between the column and the girder or the roof are rigid. All are rigid. So all these are rigid joints. We have two connections or two sorry foundation, two type of base. So we can have fixed base. So we have fixed base. This one example or hinged base. So we have hinged base here. So we have hinged or fixed base. So this hinged base. Okay, so this is our second type of framing, in-plane framing system. In this system, the roof members can be rolled or welded plate section or trusses. The frames designed for base fixity rely on the rigidity of the foundation, particularly on rotational rigidity. So the type of footing, fixed or hinged or bent, rely on the rigidity of the foundation. The first one, or the first type is fixed base. Second type is bent base. In the fixed base, the advantage is it is structurally efficient, very economic, but footing are costly. So the problem is costly. It is economic, structure effective. This is the frame itself, but the footing are costly. For bend-based frames, the frames has flexible connection with the footing. This lateral forces through rigid knee action, commonly used in building of relatively low span to column height. The main advantage is reduced footing cost. So this is the main advantage. Advantage. Footing need not to resist large moment. So no large moment and this on this type of foot. So this is the main advantage of this type of uh, base. In Generally, the column of mill-type building are oriented such that their strong axis is parallel to the transverse direction of the building. So this leads to the building is flexible, if not unstable, in the longitudinal direction out of plane. So what this means? This means that the orientation of the column is like this. If we have IB, so this is the orientation of the column, not like this. So when you cut in the column here and have a look, the column will be oriented like this. So I can put the column here in this direction. This is what is meant by this point, the orientation of the column in this direction. So this means that if we don't use the bracing, if no bracing, the building will be unstable because nothing to resist the wind or any other lateral load in the longitudinal direction. Here is some typical longitudinal bracing systems. We have, as you know, as we will know later, that we need to use bracing in intervals. So no here, no here, no here. We don't need to use the bracing in every bay. So we use the bracing in intervals. And here is some longitudinal bracing system. The first one in A, this one or any shape of this, is wall panels between frames with minimal opening. As you can see, not much opening in this system. In B, we have wall panels but with significant opening. So if you need to do significant opening, you can use this orientation. So as you can see here, here is big opening. So these are several types of bracing. Like this is cross bracing. This also cross bracing. This is knee bracing. And this is diagonal bracing. Okay, so these are some types of bracing depending on the opening needed in the brace break. Also, there are the location of the brace should be carefully planned. This is also one important thing. To obtain the right structure solution, avoid interfering with the operational requirement. If possible, bracing should be situated close to the position where first frames will be erected to facilitate overall building erection. So the best practice is to keep the position of the bracing close to the first frame will be erected to facilitate the erection. The bracing in the plane of the roof is also required to transfer wind load acting on end walls to vertical bracing. So horizontal or roof bracing is also required. Roof bracing is usually designed in the form of horizontal truss or wind girder. So these are the wind in plan, the wind bracing in plan. So this is plan view. So this is the bracing. In the low-rise framing system, low-rise industrial building, we have two types, A and B, C, and so on. We have industrial building framing system. A is roof truss and cantilever column, as we mentioned earlier. B is a portal frame. So these two are commonly, we have used them before. So these are the framing systems. C and E, C, F all are bracing systems. So C is longitudinal X cross bracing. D is K bracing or knee bracing. E is longitudinal cantilever columns with cross bracing. And F for the bottom frames are used for single story structure with rigid beam to column connection, such that the original angle between intersecting member and moment resistance connection are virtually unchanging. So the connection between beam and column are rigid. This type of system used extensively for framing single-story buildings like warehouses and factories, resist vertical and lateral load through the framing action. When fixed bases are used, structural action is enhanced because all members are fully utilized, but the high cost of the larger footing often precludes their use. Knee joint has a prime importance in this type of structure. There are some types of knee joints or knee connections. The first one, A, is the field welded connection. So this connection is welded in situ. The second one is lateral bracing, A and B. So there is lateral bracing connection of A and B. The third photo shows the bolted moment and end plate connection. So this is the moment end plate connection. And the last one is a stub connection. And here is some types of portal frames. I have several types of portal frames. Type A is constant cross section. So the cross section of the column and rafter are same. B to D, stubborn members. So this one. The members are stubborn, so the cross section is changing, not same. E is portal frame with column crane runway brackets. So this is the brackets. F is a stepped column portal frame. So as you can see here, there is a step to carry the crane. G, separate crane post, as you can see here. H, rafter hung crane runway. So here the crane runway is hanged by the rafter. I to K, multiple base frame. So I, J, K are multiple base portal frames. So these are several types of portal frames. The advantage of portal frames are simple in design, long span and fast track construction, lightweight compared to other structures, so will lead to lighter foundation. No cross bracing required, so continuous construction. Saving on steel material, more efficient to use the capacity of the structure, especially when with fixed raise. Less maintenance, cost effective for short to medium span frames. Advantage over truss system, low structure depth, clean appearance, and ease of coating and maintenance. The second point of portal frame is sizing and analysis of portal frame. There are some sophisticated structural and software packages already available, like MicroStran, Multi-Frame, Space Gas, and Flan 7, ready to use for steel structure or portal frame, which can rapidly handle linear and linear analysis with design along with many functions. The table below consider the first order analysis. However, the Sona standard 4100 requires such a frame include second order effects where relevant. So this table is the linear analysis formulas of H, V, and M. So this is H, V, and M. And in this two figure, data for preliminary sizing of hinged base frame. So this frame is hinged or bent. Usual range of rafter depths in figure A. So if the span is, let's say, 10 meters, and the spacing is S8, so the depth will be around 300 centimeters. In figure B, dead load for after expressed in kilonewton per meter, design height to eaves is 15, wind is 15. So for these two conditions, this will be the dead load. So again, if this is 10, this is 8. So this is the dead load. So dead load is around 0.8 kilonewton per square meter. It's just an overview or quick example about how to size the frame sections and how to assume the dead load. In this chart as well, figure 113 is design chart to evaluate the key design action effect to portal frame, to hinge or to bend portal frame. Okay. In this video, there is a video here about example of construction of steel portal frame. So it will be good to have a look at this video. The next point we have is steel frame for low-rise building. The framing system for low-rise building are two-way braced or core braced using concrete or steel core with steel gravity frame and simple connection. Also, we have one-way braced using rigid frame action in other direction or two-way rigid frame with no braking. So these are the steel frames for low-rise building, one story or more. As you can see in figure A, this two example of two-way brace. Figure B, example of two-way rigid frames with no bracing. In figure C, this is an example of moment resistant frame or rigid frame. In figure D, core braced using, in this example, this shear wall or concrete core. In figure E is a one-way braced frame with bracing bay in the middle. The two-way braced and core braced type often used for their low unit cost and simple construction. Beam and beam to column connection are flexible end plate or web-sided plate. For rigid frames featuring two-way rigidity, require more steel material, so costly, permit fewer restriction in layout and function, sometimes employed in severe earthquake zone due to higher ductility. So this is one of the advantage is higher ductility. So severe earthquake zone. Framing connection for low-rise building, often field bolted type, so bolted, welded in situ is not favored by erectors because so welding is not very favorable, very favorable. because this couldn't be probably carried out without staging and weather shields. It can cause delays in construction, stringent inspection, and consequent frequent remedying of defects required. So it needs more effort, so the bolted connection are more favorable in the low-rise building. This figure 115, is simple connection design method. In figure A, this is typical braced multi-story frame, as you can see, multi-story with bracing system. In figure B, this is simple connection eccentricity. In figure C, depending on distribution of the between the upper and lower column, upper and lower column. The next point we have is the tall and we can call it high-rise building. So tall high-rise building. The definition of tall building is building that can be considered tall when it is more than 30 stories. This is the general definition. The engineering definition is when the building structure must resist significant lateral forces, wind or earthquake, in addition to resisting gravity forces. There are two main design considerations for tall buildings. Number one is lateral forces developed by the wind moment structure. Number two is the gravity forces developed by the weight gravity structure. So these two considerations need to be keep in mind while designing a tall building. And this is the forces on tall building. And our problem in the lateral load is sway or drift. And so what is the significance of wind load? Significance of wind load in tall building. So in high-rise building, the efficiency of structures can be compared roughly by weight per unit floor area. Weight of floor framing is influenced mainly by floor span, but virtually independent of building height. The column weight, considering only gravity load, is proportional to height. Building up to 10 stories designed for gravity load can usually accommodate wind loading without any increase in member size. When more than 10 stories, additional material required to resist wind load and increase non-linearly with height. So wind load are more significant when building exceeds 10 stories. And this figure is showing the significance of weight in tall buildings. So as you can see, the number of floors, when the number of floors increase up to like level is the like you can see that is close up to here, say here. But you can see here how much the gap is at 100 stories. So this is the column and this is the wind depressing. So the wind is more significant or the size of the sections are mainly relying on the wind, not the gravity load. Structure systems for tall buildings. Tall buildings can be organized with two separated but connected structure systems, one to react to each different force dimension, or single structure system can be organized to resist both sets of forces simultaneously. The key goal is structure efficiency. Weight. Adequate stiffness is provided, allowing the main frame to be designed as simple construction. There are two types of tall building. Raised sway stiffness provided by internal walls, lift shafts or cross-braced. Unbraced or sway is resisted by the inherent bending stiffness of the rigid frame action. So these are two different concepts of the system in tool building. So in figure A, as you can see, this is the brace system. In figure B, it is unbraced. So all the lateral loads will be resisted by the framing action between beam and column. In early tool building, steel frames were organized to resist the gravity loads. In early tool building, steel frames were organized to resist the gravity loads. Relatively straightforward system column primary and secondary beams were used. This type of frames is efficient to resist the gravity loads. The wind loads induced moments were resisted by connection between beams and columns. Additional strength and stiffness offered by masonry increment to assist it in carrying the moment by wind, making strong structural connection to cope with the moment forces increases the weight of the building. This increase magnitude of gravity loads cause inefficiency and unnecessary costs. This is example of tall building, the Home Insurance Building in Chicago and the Empire State Building in New York. There is concept, same concept in steel and concrete structure, which is called frame and core approach. In this, in a steel structure, the truss, shear truss frames, the trusses resist the moment from lateral load. The frame resists the moment from or resists the gravity load. But in concrete, the concept of frame and core approach in concrete, shear wall or core braced frames, the core and walls resist the moment and the frame resists the gravity force. Truss or core resist the moment instead of relying on connection between column and beams. Connections are designed primarily around gravity force, removes the weight from structure. Removing weight improves efficiency and this in turn reduces cost. These factors allow greater height to be reached for the same cost or the same weight of structure. And this figure, a comparison between the frame and core approach in steel structure and the frame and core approach in concrete structure in figure 120. As you can see here, in the core is from steel called like shear truss frame. In concrete, there is a concrete core. There are there are other production system for taller buildings, not only the frame and core approach. So other types like outriggers and built trusses, and other one is tube and bonded tube and tube. There are several types of system or structure system used for tall buildings. There are two examples of them here, outriggers and built trusses, and tube and bonded tube. Here is the cross section of the outriggers and built truss. In this system, the building is surrounding by outriggers and built trusses that help to resist to like surround the building to resist more lateral loads. And also, as you can see here, there is a central core as well, helping the system to resist the lateral load. This combination between the outriggers and built trusses with the core allow for more height or more resistance of lateral load. In figure B, there is a system of tube. This is a basic one. And here is tube in tube system or bundle tube. Okay, all these systems are systems or structure system used to resist the wind load in the tall building. The last part of our first lecture is the structure steel elements. Other structure steel elements like system used in long span structure. In some buildings, large opening spaces are required for functionality of the building, like this building here. So in this building, there is a large opening required without any columns. So these requirements need like a special or specific type of structure. So in this type of structure, blade girder or trusses or space frame or arches or even cable suspended roof can be used to cover the large span with only edge column or like perimeter column, no internal column. Example of this is mall roofs, hotel ballrooms floor. Okay. In this part of the lecture, in this part, we are talking about the blade girder, which is used for large span structures. So the definition or the blade girder is a deep beam used to carry large loads over longer span. These are built up beams by welding steel plates together forming I section. So this is flange, top flange, bottom flange, and web. So all are welded. So top flange, bottom flange, and web are welded together. This is the weld between the web and the flange. Used in long span floor, heavy crane girders and bridge. Support bending moment larger than the moment capacity of any available roll section. Top and the bottom flange resist bending moment. The web resists shear. So the web resisting shear and the top and bottom flange resisting the moment. The moment capacity can be significantly increased by increasing the distance between the flanges, but the slenderness of the web is also increased, thus reducing shear buckling capacity. Intermediate stiffeners are required to prevent buckling due to bending moment or shear. The tension field action is utilized to increase the shear buckling resistance of steel web. The stiffeners are required at load points and support. So if this is the flange, top flange, bottom flange, and this is our web. So when we increase the distance between top and bottom flange, the depth, this will lead to bigger moment capacity. But the problem will be the buckling. To avoid the buckling, we will need to finish the session with intermediate stiffness. So this is how the blade girder works. To increase the moment, we need to increase the distance between the flange, but when we increase the flange, the buckling will be affected. That's why we need to use intermediate stiffeners to like increase the buckling resistance of the whip. This figure shows an example of the blade girder. As you can see here, this is the bottom flange, this is the top flange, and this is the whip. So this is the whip, top flange, bottom flange. And as you can see, all these are intermediate stiffeners. These stiffeners need to be also under any concentrated load. If we have concentrated load or supports here, so we need to use intermediate stiffener. Okay, this also a blade girder in bridge. This is a blade girder in like factory or low rise building. So these are several examples and two sections of the blade girder used in large scale. That's all for week one lecture, and thank you for listening. See you